So remember back to my first video where I said that I was too cool for 3D engines or languages with classes and garbage collection, namespaces, and things we don't really need? Yeah, well, I've thought some more about it since then, and I've humbled a bit and decided I'm just too good for operating systems at this point too. My beautifully handcrafted artisan code shall only grace the CPU if it's supported entirely by my own software. So naturally, I've made an entire operating system. But just to run Tetris. And yeah, I know what you're probably thinking here. Isn't this the guy I subscribe to because he's making video games? Well, yeah, but honestly, when I came up with the idea for this project, I just kind of had to throw my main one on the back burner because this was too good to wait. And just as a little preface for this video, it would be hours long if I tried to go into depth on absolutely everything, so I'll link some resources down in the description if you want to learn more. But with that out of the way, let's get to it. Now, normally I would start off by cracking open my IDE, slapping down a printf hello world, compiling and running to test that everything works. But without an OS to even start with, we're kind of in the wild west of computing here. No operating system, nothing that can load an executable file. Actually, the only thing we have is the BIOS, or the preloaded software that the computer runs at the start, which will get us up and running to the bare minimum, and not even that will let us start Tetris or anything that complex. The first thing we really need to write is called a bootloader. A bootloader is the first thing sort of in your control that's run on your computer as it starts up. It's basically like a preloader for any operating systems, and in our case, the first part of it lives on the first 512 bytes, or first sector of the hard disk. The first place the BIOS will look for things to run once it's done its thing and is trying to hand over control to an operating system. So to get started with our bootloader, I just threw some assembly down into a file that would basically just pause the system when it loaded and tried to build it. And tried again. And again. And tried again a few more times, and then I considered briefly giving up this project in its earliest stage. And finally, after a few hours of troubleshooting, I was finally able to get GCC to graciously accept my assembly file and have it spit out a binary. To get our emulator we'll be using though, to actually run this code, we need to create a disk image for it to use as though we're a real hard disk. This is pretty simple, and with some basic shell commands we can write a couple hundred megabytes of zeros into a file and then use the same command to take our bootloader, exactly 512 bytes in size, and toss it right at the start. Oh, and we marked it as bootable as well by putting these special bytes, hex AA55 here, so the BIOS knows that the disk is bootable and it can run code off the first sector. So after that, prepare for magic. We can boot up QEMU for the first time with our hard disk, and it stops. Cool, right? Almost done with the video at this point. Next up is to see if we can actually do anything productive, which is to say literally anything at all. So we kind of need to do the bare metal hello world equivalent and write something to the screen. To do this, we'll rely on something called an interrupt, which is sort of a way of calling into code that in this case the BIOS is already set up for us before it even loads the bootloader. Almost like a prehistoric system call with a defined API and everything. And luckily for us, if we use interrupt hex 10 with register AH set to hex E, it will print whatever character we throw in AL to the screen. And since hello world is maybe a little overdone, I think, I christened our bootloader by getting it to print Tetris time in all caps. Perfect. So now that we know our code is actually running, what's next? Well, I'm sure as hell not going to write this entire thing in assembly, so first priority is to get some C running in here. But unfortunately, that really complicates things. Remember how the BIOS has only loaded the first 512 bytes of what we put on our disk? Yeah, the rest are up to us, so if we want more than 512 bytes of code, which I think Tetris will probably take, we're gonna need to get more sectors off of the disk containing the rest of our program. So again here, thankfully, we don't actually need to interface with the disk directly, and we can use a different BIOS interrupt to get a few more sectors after our first one loaded off the disk, which is where we're gonna put the code that actually manages everything and runs the game. So you can see me in the background setting that up here. Oh, wait, pause that. You see that line there? Yeah, that one, where I typed hex 20. Yeah, that's a major mistake. Oh, but I don't know it yet. It's just one of those nice bugs that doesn't manifest until, like hours later into the project when you have no clue why the hell your code isn't working. So the cool thing is that it works for now and will only break when I'm about 20 more hours into this project and have completely forgotten about this code. which is awesome. Anyway though, putting a pin in that, since we don't have a real file system to work with, as you can see me writing in the background here, our bootloader code kinda just looks at whatever's in the next sectors on the disk after the first one and says, yeah sure, whatever bro, I'll run that, without doing any checks or anything on it, which is a highly secure way to write an operating system in a bootloader. But after some futzing around with GCC again to get it to compile C code down to a flat binary instead of a regular executable, we do basically exactly what we've done with the bootloader to get it onto our disk, except we put the C code down onto the next sectors after the bootloader, using as many as it takes since we don't care about anything else on this disk. There are no files, there's just nothing but Tetris. And we also need a lot more complicated boilerplate here to get C loading because, yeah, well, remember when I mentioned earlier that this code is actually 16-bit? Yeah, so actually all x86 processors boot in legacy mode for backwards compatibility reasons, which is awesome until you want to write any software since like 1978 and want to use more than 64 kilobytes of memory. Technically neither of which we really need for Tetris, but I mean, come on, I'm not in the mood to be writing C targeting a 16-bit machine, so we need to make the jump to 32-bit before we hop into C. So anyway, this requires a lot of complicated things like setting up a GDT and IDT, which, well, don't worry about what those are, we'll be talking about them later. Also doing something called enabling the 820 line so that we can use all of our memory, and a few other things here and there. But after that, we can finally let the CPU feast its eyes on this fancy looking instruction here and take the jump to a high-level language. And by high level, I mean C. Oh yeah, and C without a standard library, keep in mind, so we're totally on our own for everything. But still, progress. Anyway, the very first thing our wonderfully high-level C code is going to do is another little hello world where it kind of just dangerously pokes into memory at this pre-configured address to write some data there, which will magically get high to appear on the screen. And now that that was working, it was time for the first real honest-to-God game programming here, writing our graphics driver. So using the same interrupt hex 10 from earlier with the AH register set to 0 this time, we can actually request that the BIOS configure the video card in a bunch of different modes. For our case, we want clean, crisp, and colorful graphics, so we'll be rolling with a huge 320 by 200 pixels on the screen with a whopping 8-bit, fully configurable color palette. And you can see the basic driver code going down in the background here. You can see me struggling a lot messing around with some I/O ports and things, but soon enough we're able to upload our own palette to the graphics card, which uses 3 bits each for red and green and 2 bits for blue for a total of 8 bits, or 256 possible colors. And you can see the simple loops here I wrote to generate it. I threw together another few lines of code too to put together the classic full screen palette tester, and you can see that in action here. But it is just kind of, boring and lifeless. There's no motion. But how do we get, consistent motion here? Like a clock or a timer or something? Well, if you're wondering like me, boy do I have the crash course in x86 system internals for you. So interrupts, those things we use to load things from the disk and display stuff to the screen? Yeah, now that we're in 32-bit land, which we're in now, those are all gone and we need to write our own code for configuring interrupts. Which means we need something called an IDT, or interrupt descriptor table. And I won't go too deeply into detail here, but this is basically just some big lists that will tell the processor what to do when it gets an interrupt, or rather where to suspend and move execution to when an interrupt is triggered. And who triggers interrupts? Well, a lot of things, including the keyboard, any highly deadly errors like division by 0, and the one we care about right now, the Programmable Interval Timer, or PIT for short. This bad boy here cruises along at precisely 1.193192 MHz, and we can configure it to suspend execution from whatever is currently going on in the processor and run some code at regular intervals using interrupts. In our case, we're running it at 363 Hz, so 363 times per second exactly it says, hey, stop what you're doing and pay attention to me. And when we do that, we just increment a counter somewhere that says that one more tick of our 363 per second have passed. And doing a big old time warp in the background here because this took way longer to set up than you would even be able to see in the time lapse, we can use the timer in an infinite loop and boom, our demo is moving. Now that that's rolling, the next thing up is to throw something meaningful up on the screen that isn't just some pretty colors. So again, for our third and final hello world of the day, we need to be able to draw text to the screen. Now normally if I was writing a game, I would load up GIMP or Photoshop or whatever, open up an image file, make some characters, export the image, and load it up in the game to draw each character. But remember, no file system here, so no images. We have to hard code in our font directly into the binary. Lucky for us, doing a quick little Google will take us to Stack Overflow, where someone has graciously already constructed an 8x8 monospace pixel font that we can use. Looking at that though, you're probably thinking, that doesn't look much like an image. How the hell are you going to take those numbers and make characters out of them? Well, using some fancy bit fiddling techniques, we can use a font defined by 8 numbers for each glyph, 1 byte for each row, and then each of the 8 bits in each byte represent a pixel. It's a little easier to visualize actually, so this illustration will clear things up, I hope. Anyway, though, using that, and again, tossing the bits from the font directly onto some predefined address for our video memory, we have our third and final hello world for the day. And now it really is Tetris time. Well, actually, sorry, I lied there. One last backendy thing to do. So you know how we've just been throwing pixels at some memory address to draw things to the screen? Well, that's all well and good, but once we really start getting things moving, it's going to start causing some screen tearing issues. Why? Well, imagine this scenario. First, our code starts drawing something to the screen. Then the video card, operating completely independently from our code, decides it's about time to display whatever in the video buffer to the screen. Our image is only halfway drawn at this point, and then we finish drawing our image after the video card is done displaying things, and so on until we're completely out of sync with the video card. So how do we mitigate this? Well, we use the age-old technique called double buffering, where basically instead of using one frame buffer for everything we draw to the screen, we actually have two, called a front and a back buffer. The front buffer contains whatever we currently want on the screen, while the back buffer contains whatever we're currently working on drawing. When the game is done drawing, we do what's called a swap in graphics terminology and switch the pointers to the front and back buffer so the display shows whatever we're finished drawing and we can get to work in the other buffer for the next frame. This way we won't ever end up displaying an incomplete image on the screen. This is actually a lot less complicated than it sounds, so it's pretty quick to implement, and once it's done, we can draw our first block to the screen. And keep in mind here, again, we aren't able to make any sprites in an image editor. The block sprite here is actually hard-coded in, or rather generated at runtime. Here, just a few simple loops will do the trick and generate all of the colored blocks we need to get a good-looking Tetris clone going. Once we have our single block, adding in the board is simple. Internally, it's represented as a 20 by 10 array of 8 possible values, one for each possible block color, and an empty value. So if we just repeat the code that we used to render one block, changing up the position for each block, we have something that's starting to look like a real Tetris board. So time to get this to actually play Tetris. To start out, we need to get these 7 different tetraminos in here, which I'm sure you'll recognize. I decided to represent these internally almost exactly the same as the font, using a binary number for each of them, where a 1 represents a block and a 0 represents no block, with each rotation hard-coded in as well. You can see me in the background here figuring that out. What isn't depicted here is me staring at my second monitor, looking at all the tetraminos, and trying my hardest to convert these numbers from binary to hexadecimal in my head. But after that, with a few mistakes in the hexadecimal worked out, we have a falling tetramino. And back to the code to work in some rotation. Except, that doesn't look quite right. I wonder what I did wrong here. Well, after I took a good look at the Tetris wiki, it turns out I was conceptualizing the rotation entirely incorrectly, and the tetraminos actually rotate around their center. So fixing that up in the hard coding, we have a falling, rotating T-block, totally ready to do some fancy T-spins. But to get those sweet T-spins, we need to capture some user input, which means we unfortunately need a keyboard driver, which means more operating system stuff. And after a quick trip back to the Tetris wiki for some level timings from the original version of the game, and some more refactoring you can see me doing in the background here, we finally have some real Tetris-looking gameplay. Actually, wait, what the fuck is that? That doesn't look quite right. Okay, so after a little more bug fixing though, we do finally have something that really looks and plays like Tetris. But one thing is off here, and I can't really tell what it is. Something just seems wrong. Oh yeah, I'm missing the literal core gameplay mechanic. Whoops. So back to the code, and after some miserable attempts and miscalculated bounds on some mem copies, the not quite right results of which you can see here, we have lines disappearing. Next up, we can use some of the font drawing code we have from earlier to render the score, the number of lines completed, and which level the player is on. We can also use some of our block drawing functions to render the next Tetramino coming up, like some of the newer, fancy versions of Tetris do. And same deal for the rest of the UI here. I added in a cool little animated main menu made out of some tiles, and a good looking lost screen for when you inevitably fail to handle the never-ending stream of blocks. And I went on after that with some more refactoring, some more cleanup, but, well, here's where things started to get a little f***y. Remember back like 10 minutes ago when I mentioned this line back in the bootloader? Yeah, right here is around when it started to cause problems. See, because this line was hex 20 and not hex 10, only part of the whole binary for the game was actually being loaded into memory. Like the bootloader would just kind of stop halfway through loading and say, yep, you're good to go, let's run this thing. And because of the ordering of the sections of the code, this means that the code would always load just fine, but the data would sometimes be missing, which means the bug was hard to track down, to say the least. So after I lost my mind for a few hours trying to figure out what could be wrong, I finally found this one character, changed it to be correct, and could keep going. And well, once that's solved, we have Tetris, so where do we go from here? Well, there is one key component that was still lacking: music. This thing definitely needs some music. It just feels kind of wrong to play the game of Tetris without hearing the theme in the background. So music was next up. So to get this going, back in the feudal age when the first computers were being put together from rocks and fire, some dudes at IBM probably thought that it would be really nice if each computer included an onboard speaker that could make some fancy beeping noises and play music if you really just abuse the hell out of it. So obviously, to get some music going, I wrote a quick driver for the PC speaker, gave it a test, and well, that was a noise. Maybe I'll have to go back to the drawing board here. And after spending some time reading up on Wikipedia about the way sound works, the way the PC speaker works, listening to various tracks from 90s video games on it, I decided this just wasn't going to cut it. I needed to do something more intense, more ambitious. I needed to write a driver for a real, modern sound card. And by real and modern, I mean the Sound Blaster 16. This masterpiece of hardware designed from Creative has state-of-the-art tech straight out of 1997, which should be able to drive our Tetris music just fine. So I dove straight in. After wasting hours of my life learning about the PC speaker, I thought I would triple that time spent and comb through more wiki pages, 25-year-old websites, and some very old documentation to figure out how the hell to get this thing to work. But once I had poured in a sufficient amount of my life force into this code to get the driver to work, drumroll please, okay, so not quite the whole Tetris theme, but it's a start. Sounding better than the PC speaker did at least. So now for some music. Since this driver doesn't have to play any actual sound files, I wrote a little basic utility on top of it that gives us up to 8 tracks for music, each of which can play one note at a time from either a sine wave, triangle wave, or noise to give us a selection of instruments. Off the top of my head, I programmed in the melody just fine, but this just wasn't going to cut it. It definitely lacks something on its own. So I had to, of course, bust out the virtual piano here and figure out the harmony and bass. And again, this just wasn't going to do it. Like, I'm already a enough piano player as it is. Trying to do it through a computer keyboard just accentuates that. So, for the first time in channel history, it's time to bust the camera out of the computer. So let me just... Okay, maybe a few more, it'll come loose. One more hit should do it. Alright, this is pretty weird, not doing a face reveal or anything too crazy, but this is a little strange, especially considering I'm doing this voiceover in post. Anyway, I'm going to use this keyboard here to figure out the harmony and bass line for the theme. And with about a half hour of trying to remember everything from the piano lessons I took when I was a teenager, here's what we got. Not bad, huh? Really gives you that feeling like you're back in the golden days of the USSR, watching some blocks fall while you chill out on your nuclear sub hundreds of meters under the surface of the Atlantic. And I'm not trapped on a sub or anything, but I do love a good game of Tetris, so time to give this bad boy its full test run, music and all. And that's it for the video. We have a fully bootable, dependency-free operating system that can only run Tetris, which was our goal, I guess. The code, as per usual, will be available on GitHub if you want to take a look at it. Check out the README if you want to try and run it, and I will be insanely impressed if someone can get this running on some real hardware. I would have tried myself, but sadly I only have my Mac, and while I don't think Mr. Tim Apple would be too pleased if I tried to boot some bootlegged Tetris clone operating system on his pristine, unibody designed hardware. Anyway though, thank you very much for watching, and see you next time.